1 minute or less. Yeah. Yeah. Had a lot of fun. Great. Talked with Adam and a bunch of people. Adam introduced me to a lot of people. Great. Nice. That was fun. Yeah, Adam introduced you to a lot of people you said? You got Adam to introduce you to? Yeah. Yeah. How do you know Adam? From Parent. Yeah. Yeah, they're fun. Adam. Brand new. All right. Can you test the mic? Make sure that yeah. Also got to see some friends. So that was fun. What was that? Also got to see some friends in the area. Oh, nice. I don't know. First friends we're in Pennsylvania, really, other than my relatives. I don't know any humans who move there. I've had very little interaction with Carnegie Mellon, other than people I know at some point. Yeah. We have to make a lecture track. Like you don't get points or anything. Just like yeah, I think there's probably another 100 people who'd like to be here. Just out of that 100. I mean, that's how this goes, right? Oh, yeah. All right, so we do announcements. Hello.
In progress.
Hello. Good afternoon. How's everyone doing? Hey. Little feedback here. Kind of that. All right. Today is the 3rd of March. All right. We got homework and lab 6 that are due on Friday. Show of hands, how are we doing on homework 2? Good. Media. Bad. All right. Kind of bad. Definitely get working on it soon if you haven't started. This is kind of a challenging homework. Am I still echoing? Yeah. Is this on? This is unmuted. This is why. All right. How's this? No. Okay, that one should be unmuted. Yeah. This one should be. Yeah. All right. All right. That's also kind of all. Okay, great. All right. Thanks, Jess.
All righty. Hi, everybody. Let's share some screens. Okay. All right. Hello, everybody. All right. So today we talk about binary search trees, and we're going to be addressing the elephant in the room about how these trees can have variable sizes. But before we do that, I want to revisit big theta, big omega, actually just big O and big theta, and think about binary search tree height as a warm-up for today. Okay. It's a common student question, which is, well, like I look on the internet and there's big O, there's big theta. If we have big theta, why do we also need big O? And the answer is basically the same thing as if we have an equal sign, why do we need a less than or equals? Okay, so that's more or less directly analogous. And so I'm going to dig in on this point, building intuition about BSTs and reinforcing this little subtle point. So first, we're going to talk about the height of binary search trees. And trees are going to range from best case bushy, which we have over here on the left, and we have worst case spindly is the word I'm going to use. And the difference in terms of performance is dramatic. So a bushy tree, as we saw last time, you can get through the tree in a logarithmic amount of time in terms of the number of nodes, whereas with the spindly tree, things could be a little harder. So question for you. Let's say h of n. Remember that, as Justin talked about, big theta and big O, they could be used for any mathematical function. And so let's say that h of n is the height of a tree with n nodes. I really have two h of n's here. I have one h of n for a bushy tree, and I have another h of n for a spindly tree. I'd like you to give me the answer for what the number of, or sorry, the height of the tree is as a function of the number of nodes. Our warm-up of the day. Actually, we have 4 warm-ups of the day. Let me turn off my walking app so I can check your progress. You can chat with your neighbor if you like. I'm going to wait a little more time. Okay. You guys are in 93% agreement and have the right idea, which is that this one's logarithmic and the other one's linear. Okay. Now, this is pertinent because if you built a BST set using the techniques from the previous lecture and as you'll implement in lab, if you have a tree that looks like this, it's spindly tree, it's still a tree, but if you have a spindly tree, it's going to take linear time, which is quite bad for your operations. Next question for you. Which of these statements is true? Is the worst case binary search tree height theta n? Is the height big O of n? Is the height big O of n squared? Which are true? And do you have a question?
Yeah.
Yeah. Yeah, sure. I'll take the question first. Yeah.
So you can ask what big data is. What big data is?
Yeah.
Login.
Yeah.
Big O, something different.
Good question. We're going to be thinking about big O here. This question kind of gets at that. Yeah. Right. This is based on what we saw Friday. Yeah. All possible binary search trees. What do you guys think? I'm gonna wait until I get as many answers as I had the first time. Again, feel free to chat. Okay, I'm about to give it away. Okay, turns out they're all right. So all 3 of them are true. Most of you did not think that C was true. But the way to think about it, when I translate it into English, it's the height of a binary search tree is less than or equal to n squared. It is a true statement. It's not the most precise statement, but it is true. Okay. Now, this is something that most people on the internet get wrong. In fact, if you go to the Big O cheat sheet, last time I looked a while ago, they used Big O, theta, and omega in sort of a funky way. But here, literally, the mathematical meaning of Big O, that third statement is true. Any questions about that? Okay. Because remember, Big O is just less than or equal to, informally. Okay. Which statement is more informative now? This is your third question. Okay. What do you think? There's only 2 more of these annoying questions. Well, this one and one more. Oh, phone. You're really interested in. That was strange. I didn't define informative for you, but I hope I could convince you of the right answer in a moment, as I see it. All right, I'm at the same number of responses as before, so I'm gonna keep going. I'm gonna say theta in is more informative, and I'm gonna give you an analogy. Now, the reason, like, just in terms of this specific problem, that I think that this statement's more informative, if I say that the worst case order of growth is in, that's more informative than saying the height is less than or equal to n. It's a more precise statement. It tells you more. Here's the second question. Which statement gives you more information about a hotel? A, the most expensive room in the hotel is $630 a night, or every room in the hotel is less than or equal to $639 a night. Think about the space of all possible hotels. Hmm. I'll wait for 8 more responses. Okay, we're still at about 25% who disagree with me on this, and that is okay. But let me argue why I think A is a more informative statement. So the Ritz-Carlton Lake Tahoe is it was $639 a night when I made the slide. It's probably more now. These are two rooms, or two hotels where it is true that all rooms are less than or equal to $639 a night. So the Ritz-Carlton Lake Tahoe is true, and also the Comanche Motel in Fort Stockton, Texas, where I stayed on my way to move to California when I went to grad school. They had Merle Haggard karaoke, and they just did the whole CD all the way through. It was great. I loved it. Anyway, but the average room was much cheaper. I think we paid $30 for our room. Okay. So it is true with theta and O, yeah? I would say more generally that theta is just it has nothing to do with necessarily cases, best case, worst case, anything. It's just any mathematical function that grows as a function of some variable, you can throw in some thetas. Yeah, you disagree?
We're technically abusing the fact
Yeah.
notation because we're not defining a single function, right?
Right.
For a given n, we have multiple possible outputs. So it's not technically a function in that case.
Right, but if you say worst case, that's whenever once you say worst case, now you're condensing it into like one really specific thing.
One specific function, which
Right.
does allow you.
Right.
It is.
Here.
Yeah, if you are saying that like we're kind of like abusing the notation a bit here by claiming that there's like multiple possible runtimes for a given value of n. But if you have like defined worst case, then you're defining one specific value of runtime for every single value of n. That gets you an actual function that you can use proper data notation on.
Another way to put it is I could give you the best case in theta notation, and I could give you the worst case in theta notation, and I give you the average case in theta notation. And I could be like among all the users who actually I'll just stop there. Yeah.
Yeah.
So theta is, yeah, if you have a specific function, theta could be applied to it. So I think of worst case and best case as totally orthogonal to theta versus O versus omega. Yeah. So binary search tree height is all 4 of these things. It's big O of n. It's less than or equal to n. It's theta log n in the best case. That's the best case. So in the best case, the very specific situation we're talking about, I can tell you its height grows logarithmically with n, and exactly so. It's theta n in the worst case. That's the spindly tree, and it's big O of n squared. These middle 2 statements are more informative, but they're a little clumsy to say, right? I have to be like, in the best case, it's theta log n. And so if you just wanted a concise thing to say about binary search tree height, I guess you could say big O of n. If you just wanted to say, if you wanted to have a blanket statement for all trees, you'd have to use O. The only way I can start talking about thetas is now narrowing the possibilities of possible trees. Okay. So again, big O is not the same thing as worst case. And as an example, we have that binary search tree heights are, of course, big O of n squared. But that's just like a big bound that doesn't matter. Okay. Big O, I will say, is often used as a shorthand for worst case. And often people will say it's big O of yada yada. And they're really what they should be saying more precisely is in the worst case, it's theta something. This takes a while to digest. And I would say most people who have I would say a casual to moderately strong understanding of asymptotics still mess this up. So if you can come out of the class by the end feeling comfortable with these four statements, great. You'll be better off than most people on the internet who talk about asymptotics. Okay. Any other questions about this? Yeah, cool. This was very confusing to me when I learned all this stuff. So hopefully these four statements at the top helps. Yeah.
It's like convention though, if someone tells you my algorithm is O whatever, does that hold up like
Yeah, so by convention, if someone says my algorithm is big O of whatever n cubed, probably what they mean is it's big theta n cubed in the worst case. That's hopefully what it is. But it could also mean I actually don't know the runtime, but I know it's bound above by n cubed. Because sometimes we don't know the runtimes of something, but we can tell that it's bound below or bound above by something.
We did that with this point sets.
so it could just be possible.
Right. Well, not just messing with you. Maybe they just don't know how to mathematically show it. Right. It might be easier to prove the n cubed than the actual like n to the 2.8 or whatever.
We will show you later an algorithm
Yeah.
that we know is optimal. We know it's bounded above, I don't know, some function, but we don't know the exact data bound.
Right. Some of you just don't know. So big O is still a useful idea. I mean, going back to what you said, it allows us to make these nice blanket statements. Like we could say binary search is big O of log n instead of saying binary search is theta log n in the worst case. That's just easier to say often. And again, sometimes we don't know the exact runtime, so we use big O to give an upper bound. So for example, the runtime for finding the shortest route that goes to all world cities, we know that the runtime of the best possible algorithm is big O of 2 to the n. There might be some faster way, but nobody knows it yet. And then the other thing is it's easier to write proofs for big O than big theta. So for example, if you want to talk about merge sort, it's lazier to think in terms of big O than big theta. Okay. So binary search tree, I would say, is both of these things, theta log n and theta n. This is really what I want to think about as we go into the next part of the lecture, other than our big O reminder. So let's start digging into binary search tree operations. Okay. So again, if you were confused, I would say debate these things with, I don't know, TA and office hours or each other. And if you can get those four things in your head, great. But for now, the two things I want you to have in your head that hopefully you do believe me is that best case we're theta log n and for heights of a binary search tree, and in the worst case we're theta n. So let's think about this binary search tree. The height of a binary search tree is important, but so too is the average depth. And what I mean by that is the depth of a node in a tree is how far it is from the root. So the depth of the root is 0. Okay, the depth of V is 1. The depth of G on the slide is 2. Okay. And so the average depth of a tree tells you something about a random operation on the tree and how long it's likely to take. So the height of this tree is 4, and the average depth is some other number. So in this particular case, you can work out the math. It turns out to be 2.35. That tells you if I do a random compare operation, or sorry, contains operation, imagining this is implementing a set, and we know, and the item belongs to the tree, that would be the average amount of time it takes to find it. Okay. So the height of the tree you could think about tells you the worst case runtime to find something. And then the average depth tells you the average case runtime to find something. Makes sense? So both of those quantities make some natural sense. And we'll be talking about these properties of trees as we go forwards. Suppose we want to build a binary search tree out of these numbers. I want you to think for a moment, in what order would I insert them to get this tree? Could I ever actually get that? Or is that just like a hypothetical that's not worth being afraid of? Likewise, what would be the insertion order to get this tree based on what we saw Friday? I'll give you guys 40 seconds or so to think about it. And by add operations, I mean like you add, then you add. right, spindly tree. How would you get 1 as the root? What would you insert first? 1. Okay, then could you get this? What would you insert? 2, 3, 4, 5, 6, 7. So if you insert in increasing order, you end up with a bad situation. Here, what do you insert first? 4, then 2, dos, yeah. 6, okay, and so forth, right? So those 2 trees can really happen. And what that means is that the performance of the binary search tree set that we built on Friday is dependent on the order you insert things, which is fine, except that in one of the cases, it's actually really bad performance. If it was like, oh, sometimes it's login and sometimes it's 2 login, we wouldn't really care. But the fact it can range from n to login is quite bad. Makes sense. You don't want a data structure that has an adversarial input that makes it behave badly. Okay. So, well, I mean, yeah, I can tell that, yes, it's possible to get a worst case tree, but does that actually ever really happen? Let's say I'm building, I don't know, a social media application. I have people signing up like Reddit and people are joining and I store all the usernames in a big old set. Okay. Well, maybe it doesn't actually happen in real life. So let's think about what happens with randomized binary search trees. This is a video showing randomized insertions into a binary search tree, just inserting totally random items. And you can see that as I'm inserting the tree, I mean, it's not perfect, but I don't know. Does it feel, what's the feeling to you? Spindly, bushy? Feels bushy, right? And so you can do experiments like this. And in the early days, whenever computer science research was brand new, maybe you could even publish something about that. But, you know, sort of this easy stones are unturned. But you can show that it is indeed a bushy tree. I'll say more about that in a moment. Okay. So it turns out that random trees have a theta log n average depth and height. So in other words, random trees are bushy. So if you have random people signing up for, say, Reddit, then you'll be fine if you're storing it in a tree set, as long as people sign up in a random order. Now, if you have a bundle of users who started from early in the alphabet and went to the letter Z, then you could have trouble, but randomized would not be a problem. Okay. You could do a more careful mathematical analysis than just running simulations. You could show that if you insert n distinct keys into a binary search tree, the average depth is 2 natural log n. And I'm using this so-called tilde notation. We didn't talk about that, just did not present it. But it's the same thing as theta, except you don't throw away that leading constant. Okay, so, but I mean, basically it's going to be log n. But you can show it's tilde 2 natural log n. And so the average runtime for a contains operation on a tree where you have random inserts will indeed be log n. Okay. Then we also have tree height. If we want to know the worst case, in 2003, there was a paper which showed, surprisingly late, that if you insert indistinct keys into a tree in random order, the expected tree height is 4.311 natural log n. And this is a much messier proof. Okay. All right. And so that means, again, that the worst case runtime, if you have random inserts, is going to be theta log n. Okay. Now, that proof is much more complicated, but you can go check it out if you're curious. Okay. So what we have now is the following. Worst case is n, insert in 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We have best case log n, and we also have random case log n. And it might feel like at first, great, like random's good enough. There's lots of cases in computer science where we rely on randomness to get good performance, but we'll run into problems for 2 reasons. One of them is that in real world applications, we have both insertion and deletion, and even deletion can get us in trouble. But the other thing is we can't necessarily rely on random insertion. Okay? One thing you can show, by the way, is that if you do random inserts and deletes, there's a question like last time someone asked, when we delete, how do we know if we should pick the predecessor or the successor? Turns out that if you randomly pick between them, like you do predecessor one time, successor other times, that the average height of the tree, including deletion, will stay log n height. If you randomly pick between predecessor and successor, if you only ever use the predecessor or successor, like you always use successor, then it'll start looking square root e instead of log e. Not on the slide, but there you go. Okay. Okay. So there's some good news. Binary search trees have great performance if we insert items randomly. The performance is log n per operation. But the bad news is that we can't always insert our items in a random order. Also, I just realized I misspoke. I said we have 2 problems. One problem I just described is actually solvable by randomly picking between predecessor and successor. But actually, the most fundamental reason, the reason we can't rely on this log-in forever and feel good about it, is we can't always insert our items in a random order. So question for you, why can't you do that? It's not that it will violate the order of the binary search tree property, because we'll always put it in the correct place. Yeah. Right. For example, you may have a time-based system where the key is the timestamp that the item arrives. More generally, we don't have all the data at once, right? Like data comes at us over time. We don't have control over what we're going to get. If you have all the data in advance, then sure, you can just insert it into this tree and maybe define some order where you don't get a messy situation like this. But in general, like you can't guarantee safety by doing random order in the real world because it's data coming at you. And it may be that whatever you're using as your search key, the things you get might be in increasing order in some way. And some obvious example that you brought up was this notion of storing dates of events. What's that?
Like certain numbers. Possible like
a heap is a different data structure that we'll talk about at a future date, but it won't be useful for this purpose, for lookup. So we're going to do something totally different. We're going to talk about something called a B tree, which will be a stepping stone to a red-black tree, which we'll talk about Wednesday. So we want to try and avoid tree imbalance. And the way we're going to do that is, oh, go ahead. Yeah.
the tree always perfectly balanced.
We don't really care that the tree is perfectly balanced. We just care that it is going to be log height, or log average depth, I guess I should say. So we've seen trees where you don't get perfect balance, but we're going to try and get them as close as we can. Okay, so on this top part, I have a nicely, beautifully balanced tree, but we have more data coming in, 17, then 18, then 19. Wait, we can't change the future. We can't change the fact that someone's going to give us numbers that are in increasing order from here. So the problem we're facing is that if we add new leaves to our tree, remember a leaf is a tree with no child, then we're going to run into trouble. So a crazy idea is let's just not add leaves to the bottom. Okay, that's where we're going to start. That's how we're going to derive this idea. If we do that, the tree will never get imbalanced because we won't be able to add more things hanging off the edge. So there's a question, what should we do with incoming keys? Well, my first approach is I'm just going to overstuff the existing leaf nodes. What I mean by that is that when I insert 17, I'm going to allow this node to contain 2 numbers. Then I'm going to allow it to contain 3 numbers and so forth. If I do this, hopefully you agree that the height is just going to stay, in this case, fixed. Doesn't matter how many things I add, I'm just going to end up with more and more stuff in my leaf nodes. Now, obviously, that's not the whole answer, otherwise lecture's over. So we're going to run into some trouble. If we keep adding numbers, this will work. I mean, you can make an overstuffed tree, and it would be a logically consistent data structure, but it's really weird, okay? So imagine that we try to call contains 18. How would it work? So we look at the root, is 13 18? No, so which way should we go? Right, great. Okay, we get to 15. Is 15 18? No, so which way should we go? Right. Oh no, what do we do now? Well, we have to look through this whole node, right? So we follow those steps. And what we end up finding is that we have to somehow search our way through this list. And this list right here, I'm just saying it came in an arbitrary order. So it took me linear time in the length of this list. Okay, well, let's try and balance the individual nodes and make them a tree, do binary search, or make each node itself an ordered list, and then we do binary search. That's not what we're going to do. You could imagine trying that. We're going to do something else. Okay. The problem with this idea, I guess I should have asked you first. What is it? Like in a word, what's the problem? Yeah, you got to search the nodes. Okay, not so great. If we end up with really big nodes, searching the nodes is going to be slow. Okay. So we're going to revise this overstuffed tree approach, okay? So the height is balanced. We have a new problem, which is that the leaf nodes can get too juicy, these guys here. So the solution we're going to make here is that we're going to not tolerate just these, beautiful dolmas worth of items. We're going to say that once it gets beyond a certain size, the node cannot stay that large, okay? So I'm going to set a limit on the number of items. Let's say 3. And then if any node has more than those number of items, in this case, I said L equals 3, we're going to take an item and give it to the parent. And I'm going to say arbitrarily, it's going to be the left middle. What do I mean by left middle? 16, 17, 18, 19. Which one do you think is the left middle? 17. So we're going to take 17 and send it up. Okay. I'm going to take the 17 and pass it up to the node above. Okay. If I do that very naively, I end up with this kind of data structure, which is not quite right yet. So we have 15 and 17 here. We have 16, 18, and 19 here. But now we have a sort of funky problem. How would you describe the problem with this data structure? Say we're looking for something. Yeah?
Bigger than the left side, the left.
This right here can't be bigger than the left side because it definitely has something bigger than everything over here. What's the issue here? Like, what's ugly, like unaesthetic about this data structure? Sure.
Want to search for like 17 before our previous approach, you would just be able to go up to 15, 6, 17, 50, and you go right.
Right. Right. It's just, well, I mean, yeah, looking for the 17 is a little strange because if you're looking for 17, it's like, oh, you're bigger than 15, go right. You can look at this node as well. I mean, what I don't like about that is that here I have a mix of items that are like bigger than 15 and bigger than 17. It just doesn't feel quite right. Or maybe just simply 16 is to the right of 17, right? Like this doesn't, I mean, can you make something like this work? Probably, but it doesn't feel right to me. So let's try and think about a better way to do it. All right, so challenge for you. How do we tweak this idea to make it work? I'll give you like a minute. We're pretty close to the idea of a B tree right here. There's something I don't like about this. So try and think about what you would do. Think big. Take a minute to ponder what the nicer approach is. Very small tweak to this idea. You're not allowed to change moving the left middle. You still have to move the left middle up. You need to do something else. Good luck. So the problem you're trying to fix is that 16 is to the right of 17. Okay. Thoughts? Anybody have a weird idea somewhere in the backish or middle backish? Yeah.
16 up as well.
Move the 16 up as well. Oh, that's interesting. That could help. I do think that would be maybe a reasonable approach. I have an even better idea. I'm going to say, yes, 16 should be somewhere else, but I'm going to propose that 16 goes in its own node here. Okay. All right. So the idea is that, and this is, if it seems scary, here's the core idea. This node has 3 children. And what do you notice about these 3 different regions? So this is all the items which are what? Less than 15. These are all the items that are greater than 17. And what are these? All the items that are between 15 and 17. And that's the B tree. Holy. Yeah, there you go. It's very pretty. Yes. Say again? Oh, you just said, oh, you just made new nodes. Fair. So we started with let's not make new nodes, but here I decided, the dolmas were too juicy, so we have to split them up, right? So we started with this idea, well, we won't even add new nodes. That didn't work out for us, but we got pretty close. Okay. What I'm mimicking here is how one might imagine designing new data structures feels. You start with an ambitious goal. Don't make new leaf nodes. And then you stumble on this. Yeah. Say again? Yeah, so far we haven't changed the height of the tree. That's something nice. So even though we made some new leaf nodes, you'll notice the height is still staying constant. It'll get bigger eventually, but it's working out for us so far. Yeah.
and it can fill up every single week.
So it does seem like we're going to run into some trouble somewhere. Like we can't continue this miracle. Remember where we started? It was a tree that just had, actually, let's go back real quick. Sorry. It's worth it. We started with this tree. We've managed to add 17, 18, 19 and keep the same height of the tree. Maybe we also added 20. No, just, there we go. So we've added some new items and we've stayed relatively fixed, but we're going to run into trouble eventually and we'll get there. Okay. All right. Now this right here is a logically consistent and not so weird data structure. If I want to find 18, I say 18 is bigger than 13. Go right. 18 is bigger than 15. Okay, let's compare it versus 17. It's bigger than both. So we're going to go right again. And then we find an item. Now it is true that now we have to look at L different items per node. But what is L? What number was L? I think I said it was 3 earlier. Yeah, we can have up to 3 items in a node. And that's okay. As long as it's constant, we should hopefully be like, it's a little awkward to look at multiple items per node, but the number of items per node is bounded above by a constant. Okay. There's a question like, what if, that comes to mind maybe, which is what if a non-leaf node gets too full? Can we split that? Yes, but first let's do something else. Okay. Let's suppose we add 20 and 21. This is a check your understanding. Let's say the most number of items we're allowed is 3 items per node. What will happen here? So I'll give you guys a minute to think about this. First question is, who's going to move up in this node? The left middle, which is which number? 19. Okay, and then take it from there and try and think about it visually, or if you have paper, you can try drawing it. And you only need to draw the bottom part. Okay, so after 19 moves up, what's going to be in this node? 15, 17, 19. There's going to be all the items less than 15, all the items between 15 and 17, all the items between 17 and 19, and all the items bigger than all of them. So it'll look something like this right here. Okay. If you got that, you understand how B trees work. If you didn't yet, you'll have to get some practice. Question. How would I get 16 and 18? You get to these by knowing that when I'm looking for 16, I search through this node and I see if 16 is anywhere in there. If it's not, I go down the path that is between, like the only place it could fit. Since 16 is between 15 and 17, we'll follow this link. We haven't defined this in code, no. And we never will. Yeah. And the reason is it's a mess to define in code. That's why we're going to do the Friday night. So the question was, isn't it inefficient to have to search all of these? Not so bad. It just costs you 3 compares. That's all. So you only have to spend 3 compares to decide which path to take. Good question. We'll come back to that. Is this more efficient than just going with the worst case? Okay, let's do one more just to reinforce what's going on. If we add 25 and 26, we'll get to this state. And again, you'll want to look at these slides again. But if I add 25 and 26, what will happen is 21 will come up. You end up with this structure. Now this one's too full. Who will come up? 17, right? Okay, so it ends up there. Okay, so what's going to happen after we move the 17 up? Who's going to be between 13 and 17? 15. So we have 15, 14, and 16. The reason is these are all the items that are between 13 and 17. And then what's going to be over here? What's this node? 19, 21, right? These are the items that are bigger than 17. So we end up with 19, 21. Okay. What's good about this is the kind of mechanical stuff you guys are very good at learning through pattern matching. Okay, so I'm going to just, oh yeah, go ahead. Right, yes. Yeah, I'm not going to repeat it though. All right, what happens if the root gets too full? Okay, so this is an example where the root's going to get too full. Okay, so this is a case where we've passed, this is a sequence of inserts. Here I've passed 21 up here. Okay, we keep going. We had 24, we had 25. Who's going to get moved up? 23, we end up with a root like this. Okay. So there's a sequence of inserts that gets me to this stage. I don't expect this to make total sense to you as this is all new. But a question for you is, what happens when we split now? So who's going to move up here out of this set? 17. Now, where's it going to go? There's no one above. So what do you think is going to happen? It's a new node. It'll be a new root. So think, how many children will it have and what will the tree look like? Good luck. Yes. It works. They use it a lot in 186. It's still log in. Oh, it totally works. Yeah, it's log in all right. It's a good one. All right, ready to see what happens? Okay, this is what the tree looks like after it's split. Okay. All right, that's the B tree. So again, if you haven't fully digested that, it's fine, but hopefully you have enough texture that right after lecture, you're going to be so excited to just do this again and get it. All right. So I want to talk about some of the properties. Sorry, yes.
How do you decide to put that on the right side or the left? Like that could be the third node of 13, right?
Could be the third node of 19. You could, well, let's talk about some of the properties that happen with B trees. You can imagine drawing such a thing and then there'd be no left child of 21, but there's no sequence of inserts that would generate the tree you've described. If you follow this procedure mechanically, it'll never be that the 19's right here. Yeah, good question. Oh, yeah, right. Also, Justin points out another really important thing is that then 19 would be bigger than, it's bigger than 17, so it better be over here. Yes, that's an even better violation. All right, let's talk about B trees then. I'm going to tell you some terminology for this. So this thing is known as a B tree in real life. I'm going to call it a splitting tree for now. So my first observation is that these splitting trees where you stuff nodes and then pass items up, they have perfect balance. And then when you split the root, what will happen is every node gets pushed down exactly one level. And as a result, all of the leaves are always at the same level. So if you start with all the leaves at the same level, and the only way you get more height is by adding a new root and pushing everything down one level, it's going to stay balanced forever. Anytime you split a leaf node or an internal node, the height's not changing. We will also show soon that all operations have big O of log n time. But the nice thing we have is this nice perfect balance. The tree is always going to expand itself in this regimented way where this tree remains balanced. Now, the real name for splitting trees, as I said out loud earlier, is B trees. I think splitting trees would be a better name, but I didn't invent them. So we're stuck with the name B tree. B trees of order L equals 3 have other names. Sometimes people call them a 2, 3, 4 tree or a 2, 4 tree. I don't like either of these names so much. 2, 3, 4, awkwardly to me, that's the number of children that a node can have. So for example, in a 2, 3, 4 tree, any node can either have 2 children, 3 children, or 4 children. Why would you ever have 3 children? Well, you'd have 3 children if you have 2 items inside the node. Because then you have to have all the items that are less than, between, and to the right. B trees of order L equals 2 are also called a 2, 3 tree. We'll see those a lot in the next lecture. In the Ubiquitous B tree by Douglas Corner, the author writes that the origin of B tree has never been explained by the authors. Balanced, broad, or bushy might apply. Others say maybe B is bowing. Because of his contributions, however, the inventor, Bayer, you can call them B trees for Bayer. So nobody knows why it's called a B tree, but it's called a B tree. Now, B trees are most useful in 2 specific contexts. One is what you'll see in a data structures course like our class, where we'll pick a small L. Remember, L is the number of items you can have in a node. And that's used as a conceptually simple balanced search tree. Or you can have another one where L is very large, like, for example, thousands. And that's something you'll see in a class like 186. This is used in practice for databases or file systems. I won't say very much about it. So here's some terminology for the two examples that we've mentioned. L equals 3 and L equals 2. So L equals 2 refers to the maximum number of items you can have in each node. Notice that each node can have at most 3 children. You always have exactly 3 children if you have 2 items. And this is just the generalization to L equals 3. And sorry that the names are so confusing. This is just what people have decided. Okay.
Binary search trees, like, or trees in general, are they like sort of like, are DSTs and like trees like somewhat inefficient? Are you better off just using like DS, like disjoint sets to like?
Well, disjoint sets as a data structure can't be used for arbitrary information retrieval. So even though a disjoint set's operations are much faster, they don't have a contains operation, nor do they have a get operation. All right, let's talk about invariants of B trees briefly. So this is going to be an exercise if you're watching the video. So I encourage you, if you're watching this video, to do it. We don't have time to do it in real life. But you might find it fun to do, which is add the numbers 1 through 7 into a normal BST. You know what that's going to look like. And then try inserting into a 2-3 tree and follow all the splitting operations and see what happens. If you do this, spoiler alert, is the binary search tree will get this spindly tree. But with the 2-3 tree, what you'll get is first I add 1, then I add 2, then I add 3. At this point, the node's too full because we said L is 2. That's the max. So we'll bring the middle up. Okay, so for L equals 2, we'll just bring the middle up. There's no left middle, there's just middle. Okay, after split, you get 2, 1, 3. Then you add 4. Then you add 5. 4 goes up. Then you add 6. You add 7. Who goes up? 6. Okay, who goes up? 4. And what do you get? The perfectly balanced version of the tree. Cool. Right, isn't that very nice? And in this case, it happens to be all 1 nodes, I guess I'll call, or 2 nodes. Yeah. I have always been adding it to the, I didn't actually say that out loud. Interesting point. The child I add to is the place where we expect to find it. Makes sense? So when I added 6, I'm like, okay, is there a 6 in here? Well, it's going to be here. I don't have any children, so I'm just going to stuff it where I land, wherever the search runs out. Okay. If you'd like, there's a nice little interactive demo that I did not build. If you want to play around with this more, where you can insert items into a tree, I have it linked on the slide. And here you can, again, repeat that same process and see the tree going as you insert items. Again, another exercise that I encourage you to try later, and video viewers, you can do it. Can you find a way to insert 1 through 7 so that you get a L equals 2 tree with height 1? Maybe you want to try that. Okay. Well, one possible answer is 2, 3, 4, 5, 6, 1, 7. If you make that insertion, you get this height 1 tree. Okay. Bottom line, though, is that no matter what order you try to insert things in, the resulting B tree is always going to be bushy. It might vary in height a little bit, but overall, you'll get a bushy tree. Okay. So because of, and why is that true? Okay. So because of the way B trees are constructed, we get 2 nice invariants. The first is that all of the leaves have to be the same distance from the root. Okay. The next invariant is that a non-leaf node with k items has to have k plus 1 children. So for example, this tree is impossible for a couple of different reasons. One is that these 2 leaves are a different distance from the source. And then here's another problem, which is that this node has 2 items, but has only 1 child. It really should have 3 children. We have not proven these. I'm not going to prove them. But you can try thinking them through. It's basically an inductive proof, which is assume you have a tree that already has these properties. Any operation I apply, these properties remain. Okay. But I'm going to ask you to mostly feel it in your heart that this should be balanced, that these invariants should be maintained, and then we can get nice runtime. So these invariants guarantee that our tree is always, always bushy. And so I'll talk you through that briefly. So here's sort of the 2 extremes of what a B tree can look like. at one extreme, you have a tree. I'm going to do the L equals 2 case where there's at most 2 items per node. So in the best case, you get a tree like this where we have this branching factor of 3. So we have a root, and then we have 3 children, and each of those has 3 children, and so forth. And then this is the near worst case, right? Do you guys agree with me that if all the leaves are the same distance from the root, and every node has the number of items it has plus 1's children, do you get a sense that these are kind of the worst things that could happen? Hopefully. Like you'd never end up with any imbalance because of those invariants. And so what we have here is the best case and the worst case. So we see here that the height is going to grow with the logarithm base 3 of n, whereas over here it's logarithm base 2. Hopefully that feels sort of good in your heart. Okay. All right. So the runtime then, if we want to know how fast is it to actually get items out of one of these trees, the worst case number of nodes we need to look at is h plus 1. So whatever the height is, we go boop, boop, boop. And the worst number of items we need to look at per node is just L, right? Because I never need to look at more than 2 things. So in this case, what's the worst case number of items I need to look at, like total? Well, I'm saying I have, in this particular example, 1, 2, 3, what? 6, right? So 6 would be the worst case here. Okay. So the overall runtime, we could just summarize as HL. So it's the height times L, the number of items. And since the height is log n, the overall runtime will be L log n. L is just a constant, so the overall runtime is just log n. Okay, so that's the runtime for contains. Now, since I am really short on time because I went a little too long on our since I went really long on our big O, big theta thing earlier, I'm actually going to call it here, and then I'm going to pick up and kind of reemphasize some of these points. I actually only have one more slide, but I want to make sure we can get out of here, and I'm not just rushing us. Before we go, no, actually, I'm just going to call it here, and I'll just see you guys Wednesday, and we'll pick up this discussion. All right, thank you. All right. Hi.
Question on the implementation. I really like the idea where you give us but the problem is like we have to do it in a random order. When we add another conditionality of randomness, like for example, in the birthday, some kind of algorithm that can do randomness. Add it to the tree. Grab it now that it's guaranteed to be random. Decrypt it to get back.
The downside of this is that we need to be able to find them, right?
Yeah.
Random, pseudo random.
Yeah.
Right. So I map it onto the thing.
Yeah.
You could, and if you do that, it turns out there's an even better approach, which is what you just described will work and it will give you log time. But we can actually use it in with spectrum constant time instead of log time. So your approach is nice, and we will do that, and that's called hashing, what you just described. Okay. So you described the hash table, but not as a tree-based hash. That's fun. It's really have a good one. All right. Yeah. Yes. Yes. Right. Yeah. Right. Yeah. You have to have twice as many items. Yeah. Yeah. That's exactly right. So this has 15. The next tree would be 31 items. The next one after that would be 4.
It's not like the number of items here. You know, like the application you're saying the number of total nodes.
Yeah.
And I don't know how. So we're trying to make sure.
Right. I mean, I think a reasonable. Yeah, I mean that is basically the proof, more or less. Yeah, you have to have twice as many nodes to get twice as tall. Yeah, 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 yeah. Twice as many items. Yep, that's actually right. Yeah. Hi. Someone else come up with a hash table? That's funny. Yeah. 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 Got it. How would you feel? I mean, if you turned it in, I think it was fine. And if somebody yells at you later, then you could just be like, "Oh, but I talked to Josh." That's what I would do. Is it still gonna work? Yeah.
Every time we have but I'm I want to be more I realize I practice a difference. 6 minutes I need to record for the next that's why but I'll record it with that video. I'll yeah. Right. I got it. There's one more. I mean, I don't really understand how basically, I would still talk. That's sort of yes. I mean, our yeah, you can do that too, right?
Yeah, you totally can do something like that where you would just have